All right. So what we're going to do today is to look at some notes, okay, and then we'll go ahead and just practice on writing programs in assembly language, translated from C. Okay, so we'll start with control structures. So the way we're going to do it today is I have to go find my own stuff. Okay, so if you use the URL to any one of the nodes, okay, it doesn't have to be this one, but anyone. And then you just get rid of the number and just go to modules itself. It has a directory. So it's hidden here, okay? It's not easily locatable, but if you go to the directory, it will give you all the notes that I have written so far for all of my classes. So in this class, what we are doing is compiling, and I think there's only one module for that. So that will be module 0303. I learned my lesson not to host anything using the learning management system, Canvas in this case. So this way I can still have access to my stuff when Canvas is down for whatever reason. Well, in that case, I think we can take a day off because most other places will also take a day off. Hmm? Yep, I can print that out. Well, I don't really need my notes. Okay, I can actually teach entire classes for a whole week without referring back to my notes. But for your sake, it is good to have something to look at. Okay, so so when you watch the recording, you can just kind of copy the URL, and then you also have access to the same page, independent of whether Canvas is fixed or not. All right, so we're going to take a look at C control structures. Okay, so this part here is a mild reminder that this particular C code here is the same as this C code here. In other words, the B minus minus, the auto decrement of B, is not a part of the conditional statement. It is actually the statement after the conditional statement. So are we all good with that? Yes. So that it looks confusing. No, because C does not care about indentation. So for Python people transitioning to C, they would definitely think that A plus plus and B minus minus belong to the then statement. But in C, it doesn't care. It's like, okay, I can only have one and only one then statement. But that because the braces turn into a single block statement. So you have a container, which we call braces, which is also called the block statement. So the block statement is analogous to a folder, basically. So you can have as many files as you want, including zero, in the folder. But the folder takes up only one, is considered as one single file from the outside. So that's why we use braces when you have multiple statements to express in a then statement. So that's just a little reminder of the nuances of the C syntax. So now we move on to talk about this particular statement, which is relatively well used. So these are all placeholders, okay? C is really just a placeholder for the condition of a conditional statement. Block one is a placeholder for whatever you want to do if and only if C is true. And then block two is a placeholder for whatever you want to do when if and only if C is false. So are we understanding this syntax here, where C, block one, and block two, they're just placeholders. Okay, very good. So in C++ and also C and most other programming languages, they actually have a go-to statement. So the go-to statement, okay, like this one, you can look at this as the high-level version of JMPI, jump, okay, unconditional jump. They just go like, okay, where do you want me to go? It is considered as a statement, so that's why you can have a go-to as a part of a conditional statement. So whatever L1 needs to be, you can stick it wherever you want it to be. So once again, this is also kind of like it's exactly the same way as we define labels in assembly language. In fact, it's not just TTP ASM, it is almost every single assembly language. This is how you define a label. So are we good so far? All right. So you can define labels anywhere you want, as long as there's only one within the same function, it's fine. And then the go to and the label definition does they one you can have a go to before the actual definition of the label is not a problem. Okay. So now the question is, are we looking at these two pieces of code here and establishing that they are really the same? So what we want to think is to ask, when is block one going to execute in the original statement, which is this one over here? You go like, well, that's pretty clear. Block one executes if and only if C is true. Okay. So you look here and go like, okay, does this block one execute if and only if C is true? Okay. You go like, okay, let's say C is true. If C is true, what is not C? Not C is going to be false. And if not C is false, it is not going to go for the, it's not going to execute the then statement. Block one is not a part of the conditional statement. It is the block of code after the conditional statement, which in this case only occupies a single line. Is that okay? All right. So what about block two? Block two in the original structured conditional statement executes if and only if C is false. Okay, so you ask, okay, what if C is false in the second block of code? C is false, not false is going to be true, which means we execute the then statement. This is the then statement. The then statement goes to L1, which means, oh, okay, we are skipping this entire chunk of code over here. We only execute block 2 in that case. I forgot to mention one thing. There is also a go-to statement here, because without that go-to statement, block 2 is sequential to block 1, which means after block 1 is done, it will also what we call falling through. It will fall through to continue to execute block 2. So this go-to label L2, which is the label that marks the end of the original conditional statement, is actually needed. Are we good so far? All right. Hmm? Why what? Because that's just because there's nothing because block one is just a block of code, and then there's nothing stopping it from falling through. All right. So if we are not convinced, we can use online GDB, which is not working right now because it's also hosted by, guess what? AWS. Yeah, not working, right? That's okay. We always have a backup plan. There we go. Command line interface. It's pretty hard to fail this one. Oh, I can SSH to places too, right? All right, so let's go ahead and, I mean, we're just going to play with labels a little bit here, okay? Labels.c, and then we'll just go like, you don't need anything too fancy, okay? So we'll start with just a bunch of your printf statements. So we'll say printf, put string is fine, but I'm just going to use printf here. We'll say here, and we'll say there. Format, print formatted. Yep. All right, and we also need pound include, oops, pound include stdio.h, standard input output, which is what we used before C in C out, before we had streams in object-oriented programming. This is how we print stuff. All right, so I'm just going to say go to L2 and then define L2 over here. All right, so what this code is going to do, okay, has nothing conditional in it, right? So all it's going to do is to go to line 4. Line 4 says, let's go to label L2, which is on line 6, and then it's just going to print there, and that's what the program is going to do, okay? Or at least that's what I think the program should be doing. So we'll go ahead and just try this out, okay? gcc-g-o labels labels.c gdb labels. There we go. So we're going to put a breakpoint on line 4. I know the dark brown stuff is really hard to read, but you can still kind of remember the structure of the program. So we run the code. Now we get to label L, go to L2. When we single step, you can see how it skipped the printf on line 5. and L2, the label definition of L2, it just goes straight to line 7, which then, if I continue execution, it just prints there, and that concludes the execution of the program. So is that okay? All right. So now we can try something else. Okay, so we can try something like not having the go-to. Okay, so we're going to comment this out. Okay, and I'm going to put some backslash n here, which is end of line. Okay, so now the program still has a label L2 over here, but what I want to emphasize is the label definition of L2 does not change the flow of the program without a go-to. So the label definition is okay by itself. It doesn't have to be used by a go-to, but it doesn't change the flow. So that means this time it's going to print here, but then it will also print there. All right, so we'll give it a try. Okay, so we'll save this, GCC, GDB. You cannot. Well, it cannot. So the go-to and the label definition, they must be in the same function. You cannot cross functions. So you can see how in this case, it prints here and it also prints there. So that's the reason why in the code that we were looking at before, which is here, this is why, after block one, you have to have a go to label L2 because otherwise it just falls right through onto block two, which is not the behavior of the original conditional statement. Are we good? All right. So that's basically it. Okay. Or you can simplify. If there's no else, then you can simplify a little bit. Essentially, if there's no else, it simply means the block two is empty. That's all. So you can simplify the code a little bit if you do not have an else statement. Then you can say, hey, if C is false, just go straight to the end of the original conditional statement. Otherwise, if C is true, then go ahead and execute block one before we hit the end of the original statement. So are we good so far with the translation? Okay. So you go like, so what is the whole purpose? I mean, this code is ugly. Look at this. This is ugly. Okay. So the one thing that this code has as okay, there are two things. The advantage of this code is it doesn't we lose the braces. Okay, there's no need to use the braces here. In this code, the braces are mandatory when you have multiple statements in block one and block two. In this case, block one itself can have 20 statements. It doesn't matter. Block two can have another 20 statements. It also does not matter. Is that okay? No, it's not the same thing because in Python it still has the structure of the code, but it's implied by the indentation. In this case, there's no structure to the program anymore. You can, yes, yeah, yep, yep, exactly. So, so I call this process flattening because the original code is structured using braces. Okay, you can look at each level of braces as a folder, right? So in properly structured code, you use folders to help you organize your files. You never have a single folder with 20,000 files. Okay, you break it down. But in this code, we are doing exactly the opposite. We start with something that is structured, and then we basically flatten that structure and go like, okay, we're going to remove braces because the braces cannot be used in assembly language programming. That is the reason. Okay. So the whole concept of flattening the original structure code is to get rid of structure. Okay. Now, do I recommend you to use this style of programming in CISP 400 or 430? No, I don't really recommend it because your professor is going to go like, "What is this? Why do you write this code in this way?" But you can always say, "But it's not wrong." It is not wrong. but it is still in C. In other words, every single time you see a C code that looks like this, that follow this particular template, you can translate that piece of C code into this form, and it is still a valid C program. Now, that is a really important point because in the process in this class, when we translate C code into assembly code, it means the intermediate steps can be debugged using just a regular C compiler and C debugger. So it's until the very last stage where you actually have to convert it into assembly code, all the intermediate steps can still be debugged using whatever environment you guys are used to. Okay, VS Code, code blocks, GDB on the command line, online GDB, doesn't matter. You can still use those tools until the very last step. Online GDB is gone because of Amazon. I guess, oh, okay, so that means Cloudflare is AWS too. Interesting. Okay. Okay, online what? Online ID.com. Oh, okay, that's still up. Cool. Cool. Okay. Does it have C? It does. Yep. There you go. Cool. Thank you. I can give that a try too. I wonder how where the how the debugging interface works on this one. Okay. Cool. All right. All right. So back to our point here, which is right here. There we go. So do we have any questions about conditional statements? So we good with conditional statements? Okay, well, then we get to loops. So I call these pre-checking loops versus post-checking loops. Most people call them while versus do. Same thing, okay? I'd like to emphasize on the property instead of the name, okay? So in this case, we have a template of code here. C is the condition of the while loop. Block 1 is the body of the loop. So if you see a template like this in C++ or C, then you can easily translate it into something that looks like this. So let's go ahead and check out whether the two versions are the same or not. In the original version, as long as C, you evaluate C first. If C is true, then you perform block 1, and then after that you go back and re-evaluate C, and you keep doing this until C is false, and then you continue with whatever is after the while statements. Okay? In the second piece of code, we have a label L1 just defined here so that we can later get back to it, right? And then we evaluate not C, which is the negation of C, right? So we evaluate the negation of C. If the negation of C is true, which means C is false, then we go to the label L2, which marks the end of the loop. It marks the exit point of the loop. In other words, we say we are asking, instead of asking, do we have a reason to perform the another iteration, we're asking the opposite question of, do we have a reason to exit the loop? Okay. So if we do not have an reason to exit the loop, which means C is true, then we perform block 1. But after we perform block 1, we need an explicit to go back to L1 so that we reevaluate, in this case, the negation of C. Are we good so far? So go to L1 is a statement that is after the block 1 itself. So after block 1, we have an unconditional branch to go to label L1, just so that we can reevaluate the negation of C to determine whether at that point we can exit the loop or not. Thank you. So L1 is kind of like a bookmark on a user's manual. So it doesn't tell you what to do. It just tells you, oh, this is the book. This is the green post it, okay? And then on the particular page of the instruction, it might say go to whatever page that has a green sticker sticking out of it. So it's just a way for you to identify a page or a location in the manual. Yes, if we write a loop, the rest of the code. So L2 is whatever is after the loop. So whatever, because we don't know what is exactly after the loop, so I cannot tell you what is after that. So whatever is after that is marked is at L2. Yep. Yep. So I'll be good with section 3.2, which is how we basically flatten a pre-checking loop into something that does not need braces anymore. So this pair of braces is gone. There's no need for that brace. So if this block one has 40 individual statements, it's okay. You can stick it over here. It's not a problem. In other words, it is more or less a syntactical manipulation to get rid of the braces. Okay, are we good so far with a while loop? All right. So we only have one more control structure to do, which is a post-checking loop. Post-checking loop is actually the easiest. Okay, this is a do-while loop. Instead of using a while loop, the do-while loop will always perform block one first, and then they ask, do we have a reason to go back and do block one again? Okay, so the translation is literally that. Okay, it's literally just that. Okay, L1 is a label definition, and then we perform block one first before we evaluate C. If C turns out to be true, then we use the go to L1 to go back to label L1 and perform block one another time or for another iteration. Is that okay? And that's it. So I am not talking about the switch statement. I'm not going to talk about the for statement for two reasons. The for statement is the easy one because you can always translate a for statement into a while statement. Okay, because the whatever goes to the first part of the for is a is the initialization. So that part goes before the while loop. Whatever is in the middle of a while is the condition, so that can go inside the parentheses of a while. Whatever is all the way to the right-hand side inside a for loop is called a post operation. So you stick it all the way to the end of the block of code to execute and perform those operations as the last part of an iteration. So that's why your for loop is nicer to look at. It's easier for you to track what variables do we use for the condition, and we make sure those variables are either are initialized to begin with, and they are incremented or decremented or changed in some way per iteration. So other than that, a for loop is really just a eye candy version of a while loop. Okay, so for this class, we're not going for eye candy, and that's why there's no object-oriented programming either, because for the most part, object-oriented programming is also kind of eye candy-ish kind of thing. All right, so are we good so far? We have all the three control structures. Okay, all right. So the next topic is um, what about, if we have a condition that has a Boolean operator, what do we do with those? Okay, because we want to get rid of everything that assembly language cannot express. Assembly language cannot express loops. It cannot express what we see as a normal conditional statement. Okay, it also cannot express logical operations. So we go like, okay, if the original statement looked like this, okay, then we can just use something like this to replace it. So are we understanding how they work exactly the same way? The first one says, okay, the only reason why I'm going to continue execution at label L1, wherever that is C is false. If C is not false, it is as if this statement does not even exist. Is that okay? So can we emulate the same behavior but without the negation inside the condition of the conditional statement using this approach. Well, let's take a look. If C is true, then we go to label L2. Label L2 is right here, and then we just continue with whatever is next to it. In other words, if condition C is true, it is as if, oh, I take it back. Sorry, I take it back. Um, no, it is true. Okay, if C is true, we just continue. On the other hand, if C is not true, then it is not going to go to label L2. It will just fall through to go to label L1, which means we end up at label L1 if and only if C is false, which is the same behavior specified by the original code. So um, we are sacrificing statements. We're using more statements to get rid of Boolean operators in this case inside the condition. Is that okay? And the reason why we are doing it is because goto is really just a JMP. We know how to do it. Okay. Label definitions, not a problem. We know how to do that in assembly language as well. But the negation, the logical not operator, it doesn't exist in assembly language programming. So we need to get rid of those as much as we can. All right. How do we get rid of the or? So if the original statement says if C or D, those are the, if C or D is true, if and only if C or D is true, go to label L1, wherever label L1 turns out to be, then it becomes these two statements. If C is true, go to L1. If C is not true, let's go check D. If D is true, also go to L1. So do we see the connection between the first version versus the second version? Do we see that they mean exactly the same thing? Okay. How many people have heard of and remember the term it's either called short-circuited Boolean expression evaluation or lazy Boolean expression evaluation? Do you guys remember that? No? No? Shocked. Shocked. Okay. So in this case, okay, in the original form, let me go back and highlight the original form. So in the original form, if C is known to be true already, all known programming languages will not evaluate D. Because in a disjunction, if you look at the truth table, if at least one side is true, then we know the disjunction is true. There's no need to evaluate the other one. Okay. But almost every programming language that is in use right now would implement the short-circuited mechanism, which means if C is true, don't bother to evaluate D. Hmm? Say that one more time. Continue with the then statement. Yes. Yep. Now, it is important because not executing or not evaluating D in this case can be crucial because the expression that D is a placeholder for may actually do something that you don't want it to do when C is already true. So it is not it's not just an optimization of, oh, we can save some time. It is also a correctness issue, which also means the ordering of evaluation is also important because in the case of a multiplication like C times D, okay, whether you evaluate C first or D first, it doesn't matter. Okay, the programming language of C does not specify in a multiplication whether the first or the second operand should be evaluated first. The only point is we need to get to the right answer. In the case of a Boolean expression, it is always evaluated left to right. There's no exception because we have to rely on that ordering for things to work correctly. So the reason why we have short-circuited evaluation is exactly because of this. Because if C is true to begin with, we're going to go to L1. We don't even bother to go to the second line to evaluate D. All right. So in this way, I think CISP 310 is really helpful to help explain the rationale behind some of the concepts that you have learned in CISP 360, but explaining it in a much lower level mechanism, as a lower level mechanism. All right, and the last one is and. Okay, and is a little bit awkward, but not really that much different. So if the original statement says, if and only if C and D is true, then we want to go to label L1, wherever label L1 turns out to be, then it becomes like this. Okay, it's a little bit awkward because we are looking for an excuse of, can we like not do anything? Trying to be lazy, right? So if C is false, then not C is going to be true. And if not C is true, then we go straight to label L2, which is just a continuation point, which means we are not going to go to L1. Okay, so how can we possibly end up at label L1? You need C to be true. So if C is true, then the negation of C is going to be false, which means we are not going to go to label L2. So at that point, we are forced to continue to if D. So if D is actually true, then we definitely go to label L1. On the other hand, if D is false when C is true, we are still going to fall through to wherever label L2 is. Yep. hmm You apply this technique, quote unquote, recursively. Okay, give me a complicated expression. Give me something that has negation, conjunction, and disjunction in whatever nesting order you guys want. And I will try my best to write it down first, and then I'll give you the translated version. I think that's really the best way to do this. So go new. Okay, go ahead. B D. And the negation is on the outside of the and, or negating just C. Just C like this. You can use E F G H and so on. Keep going. Keep going. Like so. Okay, do we close the paren or continue? Okay. And H, like that. That's it. Okay. And then go to L1, like so. Okay. So we do this one step at a time, which means we try to figure out the last operator. Now, conjunction in this case is what we call associative, which means you can basically implicitly put parentheses around the first two, or you can also put parentheses around the second two. So which way do you want to do it? Do you want to group the first two, or do you want to group the second two? They mean exactly the same thing. I just need you guys to tell me which way you want it. The second two, like this? Okay, cool. We can do that. All right. All right. So the first thing we need to do is to figure out what is the last operator. What is the last operator that is applied in the entire expression? Hmm? Nope. Last operator, not the last value. The last operator is this and here, right? Okay. So that means we apply the and rule first. Okay. So we apply this rule. We treat C, not C as the original C. Okay. And then we treat D as this entire thing. All right. So the first attempt is to say if not C, which is not C itself, go to label L2, and then we say if D, which is this entire thing, right? Also go to this one, go to label L1. Otherwise, we put a L2 over here. Is that correct? Because all I did was really just syntactically move things around a little bit. Okay. So you look at this and go like, okay, so if you want to say double negation cancels out, and this becomes just not just if C go to L2, that's cool. Or do you want me to translate the not not into the structure that we talked about over here? Because we can do that too. You want to do it that way? Okay, this is going to look somewhat tedious. Okay, so we'll go like, so we'll say, okay, so we will look at this C as this not C here. Now we cannot use label L2 again because label L2 is already used here. So now we have to move up to label L3. Okay, so the best way for me to do it is probably just to copy and paste the entire thing and only replace the portion that I want to work with. So we have to now, replace this whole thing with go to L2, goes here, get rid of this not over here. This one has to go to L3. L3 is defined over here, and we can get rid of the extra parentheses like that. Is that okay? I just applied section 4.1 on just this single statement here. Is that okay? We go like, but Dak, line 9 looks exactly like this one, so we have to reapply that. You go like, yep, we can do that. I mean, we'll do the same thing basically as mechanically as possible because that's what your compiler is going to do. So this is going to go to L3. Now we need a L4. Okay, we define L4 to be here. Go to L4 and then get rid of this negation. So finally, we just have C in it. Yes? Okay. So now our focus can shift to this mess here. So this mess is, I, I will first remove extra parentheses that are not needed. Okay, like so. So the last operator is an AND. So we basically go back to what we had here, and then we apply this rule. Okay, so now we have to copy and paste this whole thing. Okay, and then we go like, okay, so we break it up. Okay, so we say if not this, go to a new label, and we have to go to L5 now. And L5 is going to be at the end of the entire thing. And then the second one is the if of the entire thing to go to the original label, which is L1. So L1 is going to stay here. And then we also need to get rid of another parenthesis here. Put a semicolon here. There we go. Are we good? So we look at this and go like, but Tech, we're not done. What about this negation here? So we go back to section 4.1 and reapply that. So we go, this time we have to use L6. Okay, so we go here and go like, okay, this is on its own line. And then after that, we define label L6. And then we get rid of this negation and say go to L6 here, right? And then we look at this mess here. Okay, now this mess, because of the intrinsic operator priority, it is the hidden parentheses are here. We perform conjunction first before we do a disjunction. So now we go like, okay, which template does it fit? The last operation is a disjunction. So this is the first time we go to the disjunction, section 4.2, and we're going to apply that. So, well, the good thing about 4.2 is it does not introduce additional labels. So that makes it a little bit cleaner. So we go like, if this, go to label L1, and then we go like, if the other one, we also go to label L1. Okay, just formatting right here. Okay, so we now look at this and go like, oh, tech, there's a negation inside the condition. What are we going to do about that? All right, fine. Oh, it's going to end. I mean, this is not hard, right? I mean, so we stick this next to it, define a new label, L7 this time, and then we take out this negation, go to L7. Hmm? This is what a compiler does. Okay, in fact, I'm turning you guys all into organic compilers. That's what we do in this class. So now you look at this and go like, what is the last operation? Well, it's an AND. So now you apply section 4.3, okay, which is this one here. So this is the messier one, okay, because now you have to negate the negate of F, negate the negation of F, and then that's going to go to, um, that has to go to a new label, which is L8, and L8 is going to be after this mess. So L8 has to be defined here, okay. And then this one is not negated, and it still goes to just L1. So we are pretty close to being done. So now you have double negation, right? We only take care of one negation at a time to make the code extra messy. So take out this negation, and then we go like, okay, this go to is going to go here, go to label L. Oh, this is the definition of L9, and then this one goes to L9. And we go like, oh, but there's one more negation here. Okay, we can take care of that. So that would be L10, copy, paste, and then you go like, okay, so this goes on its own line. L10 gets defined after the go to, take out the negation, and then go to L10. There we go. So now we only have the individual components inside the original Boolean expression. But do you see the approach? The approach is just a recursive way of saying, okay, what is the last operator? This one. Okay, take care of that one. Okay, whatever is left. Okay, you look at those and go like, okay, can we apply 4.1, 4.2, or 4.3? You keep doing this until nothing is applicable. Okay, so do we know how to do this? Now, do we? So, okay, let me rephrase the question. Okay, let me point out two different questions to which you probably have different answers. One, do we know how to do this mechanically? Do you want to do this? Okay, all right. But the most important part is you know how to do it, okay? Because it really is a very mechanical process. When you look at how each step is applied, it makes sense, right? The only thing is, if we start with something that's relatively complicated, like what we have here, then you just end up with something that is a little bit on the messy side. Are we good? Yep. Okay. All right, cool. And that covers pretty much everything. I think we are ready to do compiling, except I also want to point out there are simple reductions. So that means if you have a negation that is negating just a comparison, just change the comparison itself. Okay, because it is not the case that x is greater than or equal to y, it's just saying x is less than y. Make sense? Okay. Or if you have x is less than y or x is greater than y, just say that x does not equal to y. So we can apply some simplifications that does not require the mechanical translation. The more you can do it using Boolean algebra, the less you have to rely on the mechanical translation. Okay. All right. So now we focus on comparison, because back to the example that you guys gave me, basically everything in the original expression, which is the C, D, E, F, and H, G is missing. Um, they are basically all comparisons, because comparisons are not Boolean expressions. They do not involve a Boolean operator. Even though they return a Boolean value, they are not Boolean operators. So the earlier sections 4.1, 4.2, and 4.3, they can only help you take care of negation, conjunction, disjunction, but they cannot help you with comparisons. So now we look at comparisons and go like, attack. I remember, okay, this is hypothesis, right? That you guys actually remember that I said something, okay? So you guys remember that I go like when we talked about binary comparison, I said the only thing you need to know is whether x is less than y, because we can derive every other comparison using just knowing whether x is less than y. Do you guys remember that? Okay, some of you did. And then later on, we also talked about equal to, which is the z flag. It's like, oh, cool. So equal to is very easily done because we can use the z flag. So now we can just kind of go back to those statements and go like, okay, if we need to confirm x is less than y, easy peasy. There are two specific flags for this, the C flag and also the L flag. Okay. If the original comparison is to confirm x is greater than y, then we want to go someplace, well, just reverse the order. Okay. Then it becomes less than again. If the original one is trying to confirm x is less than or equal to y, then we can just convert it to x is less than y or x equals to y, because this one looks at either the C or the L flag. This one looks at the Z flag, so both are pretty easy to do. Greater than or equal to, just switch x and y, you're all done. X equals y, pretty easy to do because you can confirm with the z flag being a 1. And then x does not equal to y is the negation. So this time it does involve a Boolean operator of negation. It is the negation of x equals to y. That's the exclamation point, but in a mathematical symbol. Are we good so far? Okay, so this table in section 5 is going to give you the tools of going like, okay, I need to have a complicated or a comparison that is not just less than or equal to. Well, fine, use this table to convert everything down to less than and equal to, but with a simple Boolean operator, either or a negation. Are we good so far? All right. So now you look at general comparison. It's like, okay, fine. We apply all of these techniques and everything boils down to x, r, y, where the r is either a less than or equal to. Okay, because using all of the other techniques, we should be able to boil everything down to a value x, a value y, and then the r, which is either a less than or equal to. Are we good so far? Okay, the key point here is R is limited. It is constrained to either less than or equal to. Okay, so in that case, the code corresponding to this would be CMPXY and then JRI, whatever this R is matching this R over here. If this is less than, this R would be either a C or an L. If this is equal, then this would be a Z. And that's it. So that means we now have a way to boil everything down to assembly language instructions. We good? All right. So we're going to take a look at a few examples. Okay. We'll go ahead and I'll use my editor on the side to do this. Okay. So let's start a new tab here. There we go. So we'll start with something that's relatively simple, which is finding the maximum of two things and then store it into the third thing, okay? And we're going to use registers, okay? We have four registers, so finding the maximum of two, storing that to the third one, should be easily doable. So we'll just go and comment what the code is going to do first. So we're going to say register C is going to store the maximum of A and B. This is what we want to do. Is that okay? But only using assembly language code at the end. Okay. So the first thing is, how do we do this in regular C or C++? Yeah, that's not too hard. If A is greater than or equal to B, then we do this. Otherwise, we do this. By the way, this is the way I write code. I always write the entire structure out first and then backfill whatever is supposed to go inside the braces. So if A is greater than or equal to B, then C equals to A. Otherwise, C equals to B. That's all. Are we good so far? So now we want to apply what we have learned before, which is the first thing we need to do is to flatten the code, which means we apply section 3.1 first. Okay, Yes, I remember the section numbers. That's scary. So we apply section 3.1, which is to take care of conditional statements, okay? Because this one is just a conditional statement. So when we apply this template, this is the template that we are trying to apply. So we go like, okay, fine. Um, so one thing you can also do if you want to use this technique is to basically just leave empty spots like this, and then you just copy the entire block, right? This is block one, and then you have go to L2, then you have L1 defined here, then you have block 2 over here, and then you have L2 defined over here. And then you go back to the original code to identify what exactly is the condition. Oh, okay, the condition is A is greater than or equal to B, and that is the condition here. What is block 1? Oh, this is my entire block 1, which is the then statement of the original code. Copy, paste. So this is my block 2, which is the else case. Copy, paste over. So now I have the flattened version of the same code. Are we good so far? Okay. So you look at this code and go like, we have a pretty ugly thing here. Okay. So in this case, the negation is applied to the comparison, like so. So you look at this code and go like, do we want to go through section 4.1 and then followed by section 5 to do the conversion? Yes, I remember the section numbers. Okay, let's check, make sure the tag is not wrong. Section 4.1 is to take care of the negation, which is this negation here. And then section 5 takes care of the comparison, like simplifying the comparison of A is greater than or equal to B to, less, reverse the order, and then you do blah, blah, blah. Okay. But I can also apply something a little bit different, which is De Morgan's law. Okay, so you can call it De Morgan's law, but in this case, I think you can probably recognize that those two are the same. Okay, let me see if you can just intuitively understand that it is not the case that A is greater than or equal to B. It is really the same thing as A is less than B. Can we establish that? Yes. Okay. Well, then it makes it easy. A is less than B. It is not the case that A is greater than or equal to B. Doesn't it mean the same thing that A is less than B? Yeah, that's why I said it is not the case. Okay, so that means, okay, so if you guys agree, then we go like, okay, right? Okay. Then you look at this code and go like, can we convert this into assembly? Okay. So the biggest question is the conditional branch over here. So you look at this conditional branch and you ask, does it fit the pattern of 5.1? 5.1 says we can only deal with stuff where a register stores a value to be compared, another register stores the other value to be compared. The comparison, or R, can only be less than or equal to, okay, one of the two, and then it has to go to a particular label. You go like, okay, that meets all the requirements. Well, if it meets all the requirements, then we can do it this way. So now we go like, okay. So now we actually try to do the translation. So we now go like, okay. So we have compare AB, and then we have a J that I, yes, I intentionally just use that, okay? And now what about C equals to A? Which instruction would copy the value of register A to register C? CPR. Copy register. Okay, so we have CPR, CA. I preserve the order, so whatever register is on the left-hand side is the one that gets changed. So that means it is the same order as in C statements or C assignments. Okay, makes it easier to remember. Okay, and then what do we have? Go to L2. What is the equivalence of go to L2 in assembly language? I talked about that earlier in today's class. JMPI, yep, jump I to label L2, and then label L1 definitions are exactly the same in terms of syntax. And then we have a C equals B, which is CPRB, CB. And then we have label L2 over here. And since we are now done, we have to put a halt instruction here. Okay, you go like tech. You're forgetting on line 29. You have a illegal operation here because we do not have a j less than as an operator I. So so now we have a choice, right? I did say that it's either a C or an L. So under what situation do we use a C, and under what situation do we use an L? Correct. Yep. So it has to do with the signedness of the values that we are comparing. So you cannot determine whether it is a C or an L if I just give you the code like that. You also need one more piece of information in order to make that determination, because you need to know whether it is like this or it is like this. So between these two, we have to pick one. If it is the first one, you use L. If it is the second one, you use a C. So we'll just go ahead and say, let's just pick this one. Okay. So if we pick that one, it will be a C. All right. So this is what I claim the program is going to do. Okay. So we're gonna have to test it out. So we're gonna test it out by using the assembler. Okay. So we can copy this. Go to my assembler. Paste it in. Okay. Everything's good. Go to RAM file. Download. It's a CSV. And we'll call this find max. There we go. And then we start up Logisim. Logisim is not up yet. Load the processor file, like so. Go to the RAM component, go to load image, specify, in this case, find max.csv. The program is now loaded. Now, because all the registers are zeros, so it's not very interesting, we won't see the changes. So we want to give registers A and B some kind of value for unsigned comparison in this case. So what do you guys want to use? Yeah, let's try 8, huh? F1, okay. And then what about B? So if I use the wrong flag, F1 would be negative, right? So I think for B, we should try something that is positive regardless. So everything from 00 to 7F are positive. Hmm? EE? So E is still negative. Hmm? 4-2? Why not? But 4-2 is in the movie, they were never specific about what base that 4-2 is. So, hmm? They weren't. So assuming that they're using base 10, we should be using 2A instead, because 2A specifies the same quantity as 42. 2 times 16 is 32. 32 plus 10, which is the A, is 42. So maybe we should revise that sci-fi to use base 16 throughout the book. Yes. No, 2A in base 16. Or you can say 0x 2A because 0x is the prefix of hexadecimal. Hmm? Yep, there's a movie which is actually not bad. All right. All right. So what we expect the program to do by the time it gets to the halt instruction is register C should be the maximum between A and B. And because it is unsigned comparison using the carry flag, so that means F1 should end up in register C. Okay, so we are moving into actually writing code. which means when you're debugging code, the first thing you need to do is to figure out what the program should do. Because otherwise, you cannot compare whether the program is doing it correctly or not. Okay, so it's always important to you have to figure out what the program should do first, and then you let the program do it. All right, so I can actually do a control K inside the register bank. It will still get the job done. So let's go ahead and do it. Control K, and the program is done. F1 is indeed in register C. It works the way it's supposed to. Is that okay? So now the next question is, but this program, okay, let me go back to the code. Where did I put the program? Oh, it's inside the editor, I think. There we go. All right, so this is the code, and you go like, but tech, I really want to know how the program works and how the flags are set and blah, 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 okay? So we can actually convert it into a full-blown program so that we can actually trace the steps really one by one or instruction by instruction. So to do it that way, you have to start with a no-op instruction because of a bug inside Logisim, and then you do a LDIA with, what did we choose? F1? I don't think it would take hexadecimal, so you have to actually convert F1 into a base 10 number. So F1 is going to be 200 and let's see, 200 minus 14, 255 minus 14 is 241. LDIB is, oh, okay, it actually is 42 this time. Okay, so now the program has the built-in initialization of the registers. So I just copy this code and put it inside the command line. Actually, I have one command line that's already being used here. Okay, so we can reuse this one, Control D, and we can cat to findmax.ttpasm, paste the code, and now I can shift my directory to where I can run the code, which is called River Spider, submit temp findmax.ttpasm, and it will do all the steps for me. It will do the assembling, download the RAM file, run the program inside the emulator, upload the trace, and then also analyze the trace as a result. So this is pretty handy. There we go. So now we can go back to the assembler, but go to the analysis tab. Where's my browser? It's quicker for me to go back here to select this one. There we go. So now we go back to the analysis tab, and this is really cool. I think it's really cool because I make the tool. We can see that execution starts on line 1, which is a no-op instruction. The op code is 00. Okay, so now we go to location 01. Location 01 corresponds to the LDI instruction, and the end result is register A ends up with a value of F1 in hexadecimal. Location 3 is LDI B42, which means B ends up with a value of 2A in hexadecimal. Location 5 corresponds to line 4, which is our compare instruction. And this is the result of the compare instruction. It shows you all the flags. So it shows you that the carry flag is a 0 because 241 minus 42 does not trigger a borrow. The 0 flag is a 0 because 241 minus 42 does not get you 0, so the Z flag is a 0. It gives you a sign flag of 1 because 241 minus 42 is 199. 199 is greater than or equal to 128. So that means that the most significant bit is going to be a 1, and that's what the sign flag is. It is the most significant bit of the result. Overflow is a 0 because from the signed perspective, you have a negative number subtracting, you're subtracting a non-negative number from a negative number, but you also end up with a negative number. So overflow is a 0. We do not have an overflow situation. But because overflow is a 0, the sign flag is a 1. The exclusive or between those two is a 1. That's why the L flag is a 1. So it does go through all of those things and tell you what is the result. So now we get to row 9 of the trace. It is at location 06. It is our conditional branch of JCI. JCI says we branch to label L1 in this case if and only if the carry flag is a 1. The carry flag is not a 1. We're not branching to label L1. So if we're not branching to label L1, we are continuing execution to line 6, which is at location 08. It is the CPR instruction, which ends up copying register A, which has a value of F1, to register C. So register C ends up with a value of F1 as well. And then after that, we continue execution to location 09, which is our line 7 in the original code. It branches to label L2, and at label L2, we have a halt instruction, and we are done. So this is the usefulness of the trace. So now we can go back to the original code. Okay, so the trace is really helpful. The mechanism is super helpful because it allows you to make very small changes to the program and go like, okay, what if we are to flip these two, or better yet, we change this to a JLI, because the JLI would have reversed the actual ordering, because if you use JLI 241, the bit pattern of 241 would have been a negative value, and the negative value is always going to be less than a non-negative value. So that means JLI will take place. We will get to label L1, and then we're going to copy register B to register C before we get to the halt instruction. So that's the theory, right? We always have to figure out what the program is supposed to do before we actually confirm the execution. So we say that, and then we resubmit the program. This is You can do all this without installing this tool. It's just a lot more cumbersome without this tool. So now we have that done already. We go back to the spreadsheet, and you can see the first chunk of items are the same. So everything up to this point is the same. Even this is the same. But we can also see how the L flag is now a 1. So the JLI instruction will branch to label L1. Label L1 is where we copy register B to register C. How do we know? All you have to do is to go back to the Assemble tab. The Assemble tab shows you the line number. It shows you the location. It shows you the opcode. So now when we go to the analysis tab, the location is 06, and then it went from location 06 to 0B. So from the assemble view, it went from this location, which is our JLI instruction, to B, which is this instruction over here. So that's why it is going to copy register B to register C. And it did, okay, because register B is the one that has 2A in it. So now register C also has 2A in it. And then we just fall through to the halt instruction. That ends the execution of the program. So all of this is supposed to be, I built this entire tool so that it is easy to visualize the execution of the entire program. Okay. So if you go like, oh, this is really cool, I want to annotate this stuff here, all you have to do, okay, if you do it now, you can do so. You can go to here, and then you go to make a copy. Okay, so you have a copy of this code, and then you can use whatever is left over, in the other columns to add your own comments. You can also do this, okay, even though it's not always the best idea to do it, but you can always right click on the cell and then go to insert note. Comment will work too, but insert note is better. So you can now say this instruction doesn't do anything, but it is needed for Logisim to work. Okay. And then you can also comment the other ones, okay? Particularly this one here, okay? You can right click and go to the same place and just add a note and now say signed comparison needs the L flag, okay? Or something like that. I mean, you guys can type whatever you want. So the point is, whenever you hover over a cell that has a note in it, it will show. And I think there's a way to print it with the note included too. I'm not sure whether that can be done. Let me see. Okay, that's really tiny. And it wants to print a lot of pages. Show grid lines, show notes. Yep, it does. 5 pages, not billion. Okay, fine. 5 pages is 0.000000005 billion. Okay, happy now? What? I just did a conversion. It is still true. 5 pages is can be measured in billion of pages. It's supposed to show us the comment, but I don't see the notes, but I don't see it. Maybe it's shown somewhere else. Oh, there we go. So the notes is shown as a footnote. Not extremely helpful, but you know, but you guys know what I mean. Okay, you can use this as a tool to annotate the execution of the code so you can get a better understanding of the structure of the program. All right, so with that said, we're going to go back to Canvas and see if they have fixed the problem. Ah, Jeff, Jeff. Hmm? Hmm? Well, Jeff is now deciding whose head is going to roll. Oh, lots. It's not just because Canvas is probably not the most profit generating service on AWS. Huh? AWS. Oh, let me check whether the Los Rios stuff is still up because many of the Los Rios resources is also on AWS, including the Power Server. The Power Server is up. They only have lost connectivity to some of the backend stuff, the database. The Power Server is really just a tiny little web server. It has, I think, in virtual space, it has 8 gigs of RAM and two tiny little processors and 100 gigs of hard drive space. That's the entire server that serves easily hundreds of students every semester. That's the power of Linux, man. Huh? It hosts the website of our web classes for the most part. So we have these classes that make use of the websites. So you can click on a particular student's page and look at what the student has done with the web page, stuff like that. Yeah, it's for specific classes. Hmm? Yeah, so 400 classes do not have a forward facing, doesn't have a web interface to it. So the web facing side only has links to students who are taking CISC 310, CISW 300. Hmm? C stands for core, and then W stands for web. Yep. So it's a pretty efficient little server, but it's not affected by the issue that is currently plaguing AWS. So it means we are not going to have a lab today. I think what I'll do is to make it a homework. Okay, so it's due on Wednesday before class. So this way you guys can still kind of go through the whole motion of doing it because I think that would be super helpful. Because I don't want that part to be falling behind. So is that good? All right. But I can't set it up for the same reason that you cannot do it now. Then we'll switch to Moodle and then continue the class. I can spin up a Moodle server like that. I, well, before they use Canvas, I have been running my own Moodle server, which is another LMS, another learning management system, on a little box in my office at home for more than 10 years. And then the school decided to switch to Canvas. And with Canvas, the contract says you cannot be running any other LMS, even if it's free. The reason why they did that was because um, Canvas was their way to funnel all the student data into a um, student loan nonprofit conversion foundation. It's called the Lumina Foundation. So they collected all the student data so that they can come up with some kind of a model of some kind. Okay. And it's not even in California. So that's the reason why they had to shut down my little Boodle server, which required the district zero money. Anyhow, if this continues, I'm just gonna have to switch back to Moodle. Alrighty. Well, hmm? Yep. Alrighty. Well, since we don't have anything else to do, you are free to go. Or if you want to stay behind and ask questions, that's all good too. No, not really. You can go straight to the Moodle website. It only needs a LAMP architecture, Linux, Apache, MySQL, and PHP. Now, personally, I do not like PHP, but it's okay. Okay, it's all free. Okay, it requires very little resource to run to set up, and if you use the official um, repo, repository, um, you can get all the updates really easily, and they fix problems like almost immediately. Unlike Canvas, I reported a bug. I had one bug report when we first switched to Canvas, and that's more than 10 years ago. They still haven't fixed it. I even told them where to find the bug, and they still haven't fixed it. In Moodle, it'll be fixed like right away because I can make a local change, and then I can make the bug report upstream, and then the next day they're gonna have it fixed upstream and go like, okay, we're good. Yeah, yep. Alrighty. So I'm gonna shut down the recorder.